All right, class. Welcome to Waiting Line Analysis and Queuing Theory. This is Dr. Blake Nilsson, and I hope you all are having a great day. So, just to talk here for a second, many of us are very impatient people. We have skipped lines or went from one to another at Walmart or Costco. Or we've gone into a restaurant, or if you're like me, go to a place where there's many food options, and I don't choose based on what I want to eat. It comes down to where I can get served the quickest. Many of us have been calling to make a purchase, and the call hold time is too long, or the website goes down and we don't do it. The bottom line is businesses lose customers based on how long people have to wait. We are impatient creatures. So waiting line analysis just gives us a breakdown of how long our folks are probably going to have to wait in line. And so it is important to look at. So I've got some numbers in here for you already. Arrival rate and service rate. Hopefully you've already read through Canvas and looked at this formula sheet. This might be something good to print. These are all the formulas we need in order to understand waiting line analysis. And it is important to note here that in this class we're going into a single line with an infinite population. And what that means is it's something like a fast food restaurant or a boat dock that's letting one boat in at a time. I just went out to Antelope Island recently, and there's that one booth to let you in that's analyzing these type of lines. There are other systems that are more complex that organizations look at, but we'll keep it simple for this class and just teach you the concepts. So waiting line analysis, when you look at these two symbols, these are two things you have to figure out. How often people are arriving to your system. That's lambda is a Greek symbol, and mu is the service rate, or how often you can serve those folks. The reason this is called queuing theory, waiting line analysis, because people are in the queue as they're waiting to go on to be served, people or things. So let's just go over to our Excel sheet and break it down. So I put down, we have an arrival rate, let's just call it a local restaurant that has a drive-up window. We get 15 that arrive per hour, and we can service 20 per hour. So the first thing we want to figure out is the utilization, or how often the window or the person working the window is being working or utilized. The way I think about utilization, if I have a 100-gallon barrel and it has 36 gallons in it, then the utilization is 36%, or we're using 36% of the capacity. So we go over to the formula, we find it, we call this utilization, so that is lambda over mu. Come back over here, it's going to equal lambda divided by mu. So in other words, we are working, or our service window is going 75% of the time. Now, very important, what's the average number in line? So we're going to go back over to our formula sheet. Average number waiting in line is LQ. There's our formula. So we want to go back over to Excel. And one thing that's nice about the video and your work, hopefully you're following along with this, is when you get to the assignment or test, once you find the right formula, you can always come back and make sure you put your parentheses in the right places. So it's going to equal lambda squared. The way we square is shift 6 and square it. I'll divide it by, do need a parenthesis before. All right, so 2.25. You can always hit pause there and look at the formula to make sure you have it right. So I'm just going to go right on to the next one. The average number in the system, which is LS. You can look at your sheet. So the way we find that is going to be equal to minus B1. Okay, there's your formula. All right, now I'm going to stop here and talk about the difference in these two things. Average in line and average in system. The only difference in the two, the line is only those who are waiting to be served. The one in the system, average in the system, includes the line plus the person at the front of the line who is currently being served. So that's why the average in the system is going to be a little bit more than line when we're talking about the average line, because it includes the person being served. And the exact same for time in the line and system. So let's move down to those next two formulas. The average time in line, that is going to be WQ. It's going to equal, the nice thing is we've already figured out LQ right here. So divided by lambda. And then the same thing for WS, which is the average time in the system. It's going to equal this 3, which is WS divided by lambda. Now, before we go on any further here, these two are garbage numbers right now. 0.15 hours and 0.2 hours. Let's just assume this was per hour. Per hour. Okay. So with that in mind, we don't want to know, and we wouldn't answer, hey, what's the average time in line? Oh, it's 0.15 hours. It's just not how we talk. So the way we fix it, we're going to just go equals this. There's 60 minutes in an hour, so it's 9 minutes. And then we can just go ahead and drag that right down to figure out average time in system. And as you can see, it's an extra 3 minutes for the system, and that includes the person that is currently being served. Now, right off the bat, some of you are thinking, uh-oh, our utilization of 75%, that's no good because it means our person's only working 75% of the time. But let me show you why it's sometimes very important not to have close to 100% utilization. Let's just change this to 19, and as I do that, watch your average time in line and in the system. Alright, so it went from around, what was it, 9 or 12 minutes? Yeah, 9 and 12 to 57 minutes and an hour in the system, including when you're being served. So yeah, sure, now we're working 95% of the time, that person at the window, but our people are waiting that long. Look at our line and in the system. What's the point here? The point is that it's better to have people work a little bit less to keep your customers happy and keep things flowing throughout your business. And it's very elastic here. You can see how every number, it changes pretty drastically how long the waiting and service time is. So you don't want to get too close to 100% utilization. So just something to consider. The closer you get, it may be time to either speed up your service rate in a good way or consider adding a second line to serve your customers. So, all right, so the next part here, let's go probability line. Probability line, and just do a line from 0 to 20, or numbers from 0 to 20. Nice thing is we can highlight this and we can go and it'll tell us to 20. Alright, so and I do want the ones to be center aligned below it as well. We've done all those formulas on the sheet except that one there at the bottom, which you probably saw right at the start. The probability of exactly n number in the system. So this includes the person or thing being served. So we can find the probability of any number, including 10,000 if we wanted. We would put 10,000 in for n right there, and it would solve the probability that there's 10,000 in the system, which would be very small. We could also put a 4 in for n. What we want to do some analysis is we just want to do it all the way from 0 to 20. So that's what we're doing over here on our sheet. We are saying what's the probability of 0, 1, 2, 3, all the way up to 20. So the formula for that is going to equal 1 minus divided by B2. Okay, very important, if I didn't mention this before in the formula, even though the parentheses are next to each other, in Excel you do have to add the little time symbol here. And then B1 divided by B2 all to the Shift 6. And I can't hit that now, it's hidden, so I know that is cell B10. Alright, so you can see the formula there with the correct order of operations, and this is B10 here, so the probability of 0, so 25%. Now we already actually knew that was what that one was going to be, because the probability of 0 is the exact opposite of our utilization. This is 75, this would be 25. But now we want to drag it over to 20 without having to do the formula 20 times. The way we do that, we want this B10 to drag over to C10, then D10, but we want the B1s and the B2s to stay the same. And just to show you what I mean, if I drag it now, it gives me a value. It drug over to here, the C10s, but this 15 and 20 drug over here as well. So that's not going to work. This is where we've got to use absolute value. The way we do absolute value, we come back into our formula, and for all the B1s and B2s, I'm going to hit F4 and we'll add dollar signs to it. Now you can also add manual dollar signs and it'll do the same effect. One troubleshooting thing here, some of your computers, like F4 is music, so you have to hit function F4 to make it be F4 rather than play on your recorder or whatever. So Macs, it's a little bit different. It's Command T is the absolute value. So I hit that on all of those, and now when I drag it, you can see here it drug over to the C10, but these two stayed the same. Alright, so I'm just going to drag it over all the way now to 20. And as you can see, as you get to 20, it's a smaller probability that there's 20 in the system at any time. Alright, so now let's ask some questions about this. What's the probability of 4 in the system? That's going to be easy. It's just going to equal p to the n of 4. So let's make this percentage here. So we're going to ask a few of these. So there's a 7.91% that there's 4 in the system at any given time. All right, so get a little bit harder. Probability of less than 4. All right, so what we're asking is less than 4, so that's either 3, 2, 1, or 0. So that's going to equal the sum from 0 to 3. We hit enter, and it's 68.36% the probability that we have less than 4 in the system. All right, now for a little trickier one. Probability of more than 5. All right, so we know that's a probability from 6 all the way to infinity because it's more than 5. Here's the problem. We only went to 20, and there is a probability of 21, 22. There's a probability of 10,000, even though it's very small, all the way to infinity. So the way we have to do it, and I'll explain a little bit more here before we do it, let's just assume for a second that the probability from 0 to 4 was 60%. All right, we know that the total probability of all numbers to infinity is 1, a total of 1. So if this probability from 0 to 4 was 60 on this side to the left, then from here to the right would be 40, because the sum of these two sides have to equal 1. And so the way we do that in Excel to figure it out, it's going to equal 1 minus the sum, and we said probability of more than 5, so that's from 6 to forever, of all of these. All right, I'll click on that so you can see it again, 17.80. So that's 1 minus the sum of all of these is the same thing as from here all the way to infinity. All right, so you just have to think of it exact opposite. So we'll do one more, the probability of 2 or more. So that's really asking what's the probability of 2 all the way to infinity this way. So it's going to equal 1 minus the sum from 0 to 1. Okay, and that's 56.25 right? So once again, if it's less than 4 on this side, you just do the sum. If it's on this side going forever, you do 1 minus what you do know, and that will give you the answer. All right, one more quick thing to show you before we move on. So if you ever get to a point where you have the same amount of people or things coming as you can service, it's going to mess up absolutely all of your numbers. And the reason why is because you cannot serve them. You cannot keep up. They're not going to come in exactly perfect increments. And so as soon as one person comes late or one thing comes late, that line's going to start to grow in towards infinity very slowly. And in fact, if you have more people coming, you see all these negative numbers, it's going to mess it up even more. And the only way to fix it is to stop people or things from coming into the system to serve them. And I already went over 19, and you can see how bad that is once again. So this is waiting line analysis. This is all you need to know for your assignment and test to get you through it. I do recommend you come back and check out these formulas and go through it and double check all of your numbers before you put it in on the assignment test. And until next week, hope you have a great day.